Okay, thanks for attending. Yeah. Yeah, I know I'm losing on my audience, but yeah, that really doesn't matter because, well, I can still record my lecture. So we will be talking about the section 5 and 4, which is about the differential equations. And E T of A. So this is, well, so we'll be mainly talking about the matrix exponentials. So yeah, this is very interesting concept. So you know what, I guess you know what the matrix exponential is. Exponential function is a function, so which is defined by, well, based on the hypothesis that you guys are all attended the calculus course, and the exponential function is 1 plus x plus 1/2 factorial times x squared and right? So that is my definition of the exponential function. But interestingly enough, the same concept of the exponential exists in the world of the matrix, and we will be mostly interested in that. Okay. So first, we will consider a system of differential equations. So this is an example that we covered in the beginning of this chapter. So I have two functions, y1 and y2, and y1 derivative is some constant times y1 plus another constant times y2, and y2 derivative, yeah, it's just the same. So I mean, the rate of change of the y1 and y2, they are somehow intertwined each other. And we want to find the function in y1 and y2 satisfying these two conditions. And on top of that, also, we are not looking for we are not only looking for the solution satisfying this condition, but also we are looking for a y1 and y2 satisfying these conditions. Here, P and Q, these are some constant pre-given in your problem, and so therefore, and this condition is called the initial condition. So so that means we are looking for the functions y1 and y2 such that at time t equals to 0, y1 must be p and y2 must be q. And the question is, can I find the function y1 and y2 satisfying these conditions? Well, we already talked about that. So these systems of differential equations can be translated to this matrix in these matrices, and this guy I will call y, and this is my matrix A. So in other words, this system can be written as y prime is a matrix A times y, and this is my initial condition, which is written as y0, which is nothing but p and q. And so this is what I call the initial value problem. So the initial value problem is a very special type of differential equations satisfied with the initial condition. And I'm going to call it as my star. Well, and suppose that I have very interesting a 2x2 matrix of functions. So matrix of function means every entry is not just a Miri number, but each of the entry is actually a function depending on time t. So let us suppose that I have these 2x2 matrix, and this is a matrix of functions, and well, consisting of alpha 1, 1 to alpha 2, 2. And as you can see here, so this is a matrix and whose entry is not a just a number, but is a function depending on time t. And also let us assume that this matrix satisfying these two conditions. The first condition is the derivative of this matrix. Yeah, so it sounds very silly discussing the derivative of the matrix, but well, it's not a big deal. If you take the derivative, our definition of the matrix derivative is nothing but the entry by entry derivation. So every entry has been taken derivative, and suppose that this matrix derivative equals to this matrix, this matrix times this guy itself. Suppose that this matrix is satisfying this condition. This is what I call condition number one. And condition number two is also we assume that this matrix is satisfying this condition. Well, if you plug in t equals to 0 to each of these entries, then you're going to get the identity matrix. Okay, so suppose that suppose that this matrix is satisfying these conditions. And then the solution of the system of differential equation star. This is my star. Then the solution of then the solution of this initial value problem or this differential equation is, I claim the solution is this guy, this matrix, this matrix times the column vector consisting of the P and Q. So this is the initial condition, this guy. So I claim in this case, this is the solution of the differential equation star. Why? In order to say this, first I will need to take the derivative of this matrix, y1, y2. Taking derivative of this guy, so is the same as the taking derivative of this vector, this matrix. Well, but this is constant, so taking derivative doesn't affect too much. So I will need to take the derivative of this matrix, right? Okay. Then, well, but we are assuming that this matrix derivative is the matrix A times this matrix itself, right? And also we have declared that this guy times this is y1 and y2. Okay. So it turns out to be A times y1 and y2. Okay. So y1 prime and y2 prime is the matrix A times the y1 and y2. So this is precisely this condition, right? So, therefore, this guy is satisfying this condition. So what remains to do is also I will need to show that if I plug in t equals to 0 to this condition, to this equation, I will need to see that the y10 and y20 is precisely P and Q. But that is also very easy because if you plug in t equals to 0 here, then and then I will need to plug in t equals to 0 into this matrix. But this condition number 2 says, if t equals to 0, then this matrix is suddenly the identity matrix, right? So this is identity times P and Q. Therefore, y10 is P and y20 is Q. Therefore, this guy, this is exactly the solution that we are looking for. Okay. Okay, so this is, well, therefore, okay, the thing is, if we can find a 2x2 matrix satisfying this condition, then this is going to be automatically going to be the solution of the given the initial value problem, or given these differential equations. But the question is, can I always find such a matrix of functions? Alpha 1, alpha 1, 1, alpha 1, 2, alpha 2, 1, and alpha 2, 2. That is going to be the main topic for today's lecture. All right. Okay. So now I'm ready to spell out the definition of the matrix exponentials. I have a matrix A. So this is n by n. So I have n by n matrix A, and I want to define the matrix exponential of the matrix A. So from now on, which will be denoted by exp of A or just simply e to the A. So this is notation. So what is this? So matrix exponential is this is another n by n matrix, right? So if this guy belongs to n by n, then this guy also belongs to the n by n, right? And defined by the identity plus the matrix A times 1 over 2 factorial times A squared, 1 over 3 factorial times A to the third, and and all the way up to infinity. So if you're familiar with this infinite summation notation, then maybe I really tend to write down this guy as the summation from k from 0 to infinity of 1 over k factorial times A to the k's. Well, if you have attended Calculus 101, then I guess you are quite familiar with this expression. This is precisely the expression for the exponential function. But the only difference is the x to the k's, x to the power of k has been replaced by a to the k's. That's it, right? So because of this reason, so we say this is a matrix exponential. Right, but so we seldomly use the exp of a, but what we use most of times is we use exp of not just a, but some constant t times a. If I put this one additional t here, then if I replace this ta by t times a, then this is going to be my expression. Okay, this is going to be. So this is matrix exponentials. Okay. Now I came up with I can figure some very naturally arising questions. Is this guy exist? So in other words, so in order this guy to exist, then every entry of this matrix must be some finite number. So in other words, every entry of this guy must be convergent. Right. So we are dealing with the infinite series, and the first thing that you have to worry about in infinite series is the convergence. So and if you can find at least one entry of this guy that doesn't converge, then this guy may not exist. Okay. Now I have very interesting theorem. This theorem consists of the 4 different statements. And the statement number 1 is the matrix exponential e to the a always exists for every n by n matrix A. Right? So that means no matter which matrix A you chose, and if you plug this guy into this formula, then it is guaranteed that every entry of this matrix, every entry of this n by n matrix is guaranteed to converge. Therefore, this guy always exists. So this is very nice theorem. But I will not be proving the statement. Okay, so I'm sorry, but let me just say, let us just take the state number 1, granted. And statement number 2 is the matrix exponential of the zero matrix is the identity. Why? Yeah, this is also very obvious, because if A is the identity of the zero matrix, then all the other terms except for the first must be the zero matrix. So therefore, everything must be the identity, right? So this is also obvious. And number 3 is this is not horribly complicated, but this requires some technique that is used in the calculus 101. So which is, I'm not interested. So also, let me say this is also, let me just take this for granted too. So e to the s times a times this is matrix. This is the matrix multiplication. This matrix multiplied by that matrix is e to the s plus t times a. So this somehow really works, behaves like the real exponential function. Okay. And number 4, maybe I can try to prove this. Then this is the key property that we are looking for. So if you take the matrix exponential of this n by n matrix, so derivative with respect to the variable t, then this is a times the original matrix exponential function. Okay. All right. Why is that? So this is the quick proof. So this is my matrix exponential, and taking the derivative with respect to the t, then this tk is now t to the k minus 1, and now my index is not from 0, but it's starting from index 1, and by dividing by k factorial by k, so k factorial is now k minus 1 factorial a to the k minus 1. Now this a to the k's, I can send one factor of the a to the k's out of this summation, just like this. Okay, and now we will be changing the indices. I'm going to define new index m, which is k minus 1. Then this entire summation is now going to be this, right? So matrix A times another matrix exponential. Therefore, my claim has been proved. All right. Okay. Great. Wait. So this matrix exponential expta is precisely the matrix that we are looking for. Yeah, right? So this guy, this matrix is satisfying. So this matrix derivative is the matrix A times itself. And if you plug in t equals to 0, then it's going to be the identity, right? Great. There is a quick corollary. The matrix exponential is always non-singular matrix. Even if your matrix A be a singular matrix, but even if your matrix is a singular matrix, but E of e to the A is always non-singular. Why? Because of the property number 3. So e to the A times e to the negative A. And according to the theorem number 3, this is precisely e to the A minus A, right? Which is the zero matrix. So must be the identity. So e to the minus A is sort of a right inverse of this right inverse of the matrix, but this is a square matrix. The right inverse is automatically the left inverse. So this is precisely the inverse of the matrix. And so therefore, E to the A is an invertible matrix, so it must be non-singular. All right? Okay, good. All right. So now I want to generalize this. Let us consider the system of differential equations. So this is not 2x2 system, but this is n by n system. So this system of differential equations consists of n first order differential equations with n unknown functions with n equations. So this is a system of differential equations consisting of n equations. Also, suppose that we are looking for the solution of the system of differential equations satisfying these initial conditions. Let me suppose that these n numbers were given. Now, can I find the solution of this differential equation? Yes. Then, so y is the matrix exponential of, here this matrix A is a matrix consisting of these numbers. You can, sorry, I forgot to mention this. So you can actually find the matrix A from these equations by looking at this coefficient. Then taking the matrix exponential of this times this column vector consisting of these initial conditions should be the solution of this differential equation. Right? Oh, sorry. Also, I have to mention that. So A11, A12, A21, 22. Okay, so this matrix A is the matrix consisting of these numbers. Okay. Do I need to prove this? No. Okay. All right. Okay. So the question is, all right. So yeah, I really like the matrix exponentials. So it is kind of the master key of this system of differential equations. The question is, how do you compute this matrix? Well, a priori, the computation of the matrix exponential should be super complicated. Why? Because the matrix exponential consisting of the arbitrary power of the matrix A. And I told you that computation of the matrix, the power of matrix, it should be super complicated because it requires tons of computations. And then you are supposed to raise the arbitrary main powers of the matrix A, plus on top of that, you have to add all these matrices together. So computation of matrix exponential is usually very complicated. But the idea is, if your matrix A allows a diagonalization, then computation of the matrix exponential is now suddenly super easy. Okay. Why? Suppose that my matrix A is diagonalizable matrix. So A is n times a non-singular matrix, then I have some non-singular matrix M, which is consisting of the eigenvectors of the matrix A, whose columns are eigenvectors of matrix A. And n times the diagonal matrix lambda times n inverse should be A. This should be the diagonalization of the matrix A. And raising the power, case power of the original matrix A is n times lambda to the k times m inverse, right? Okay, so this is my matrix exponential ETA. And I am replacing a to the k's power by this expression, just like this. But this m and this m inverse, these two matrices, they are independent from the index k. So I am safe to kick these guys, these two guys out of this summation, just like this. Okay. Right? Okay. Okay. So please allow me to magnify the expression between these parentheses. So this is the summation, but now this is not just any random matrix, but this is a diagonal matrix whose diagonals are from lambda 1 to lambda n, and raising the diagonal, the power, case power of the diagonal matrix should be super easy, like this. And now you need to apply this summation to this. And can you guess the resulting matrix? Then the resulting matrix must be precisely e to the lambda 1 times t, e to the lambda 2 times t, e to the lambda n times t. Okay. Right? Great. Oh, hold on. So this is my matrix exponential. You can always, if matrix A is diagonally over matrix, then you can easily compute the matrix exponential. So this matrix of the eigenbasis of A and matrix with an inverse of that guy, and the matrix in the middle is nothing but the exponential of each of the eigenvalues of matrix A. Okay. This, well, okay. All right. So this is the matrix exponential. Also, I have an interesting theorem regarding the determinant and there is some relation between the determinant and the trace of the matrix exponentials. Well, matrix exponential is a n by n matrix, so you can find the determinant of the matrix. Okay. But so determinant is nothing but some number, right? This is just some number. And this number is exponential of, this is not matrix exponential, but this is just a regular matrix exponential that we have learned in the calculus 101. Exponential of the trace of this matrix. Do you remember the trace? What was the trace? The sum of all diagonal entries. Good. Okay, why? Because, well, this is the matrix exponential. And the determinant, the determinant is unchanged under similarity transformation, right? So determinant of this guy is the same as the determinant of this diagonal matrix, right? So, and determinant of a diagonal matrix is just nothing but the product of these diagonal entries, right? So this guy determinant is the product of each of these diagonals, like this. But this is e to the t times lambda 1 to lambda n, right? This is just regular exponential. This is an exponential function from calculus. So this guy should be this. And lambda 1 to this is the summation of sum of all eigenvalues of the matrix A. And sum of all eigenvalues is actually the trace of the matrix, right? So the claim has been proved. So now sending this t into this parenthesis. So this is trace of t times. Okay. Okay, so that's it. Now, once you have the matrix explanation, then you can solve your system of differential equations like this. So, suppose that the system of differential equation with initial conditions were given. Then my solution is the matrix exponential times the initial condition. And this is, but this matrix exponential is m times this diagonal matrix with exponential functions times m inverse times the column vector y of 0, right? But I'm going to declare this guy to be, this is m inverse times y0 to be this a column vector c. So I will just name it as c. And this matrix M is the columns of this matrix is actually the eigenvectors of the matrix A, right? So I am writing down like this. And this column vector C, which I will denote from C1 to Cn. And we all know that expanding this is C1 times e to the t times lambda 1 times the first eigenvector x1 plus Cn times e to the lambda n t times lambda n times the last eigenvector xn. So this should be your solution. So your solution vector. So your solution vector y is actually the linear combinations of eigenvectors times e to the t times of the eigenvector. Okay, so, all right. Okay. All right. Oh, sorry. Now let me turn to some examples. We are supposed to solve the system of differential equation of order 2. So this is, well, order 2 implies that this differential equation has the second derivative of function y. And we are looking for the solution of this function. Hey, we have not discussed anything about the solving system of differential equations of order 2, but you can easily transform this guy into a system, not a single equation, but a system of differential equations of order 1. How? By introducing a new function, which I will call v, and vt is defined to be the y derivative. Then y prime and v prime is y prime is just v, which is just v. I will simply omit the t. Y prime is v, and v prime is y double, which is y double prime. And is solving this equation for y double prime. So this is minus 2 times y plus 3 times y prime. But y prime was defined to be v. So please allow me to write down like this. Okay, so this is 0, 1, -2, and 3 times y and v. Okay, so y prime v prime is some matrix times y and v. So this is a very typical systems of differential equations. So this is my A. So this is y prime, and this should be my y. So y prime is A times y. So now we need to solve this system. So in order to solve the system, then first we need to find the eigenvalues and eigenvectors of this matrix A. Now this is quite a routine computation. So the characteristic polynomial of A is what is this? It's minus lambda times 3 minus lambda plus 2. So lambda square plus, no, not plus, sorry, minus, minus plus, yeah, minus 3 lambda plus 2. So lambda minus 1 and lambda minus 2 equals to 0. So I have two eigenvectors. So I have two eigenvalues. Lambda 1 is 1, and by computation, yeah, I will not be bothering this computation. So this eigenvector, and lambda 2 is, which is 2, and x2 is 1 and 2. Okay, so the solution y and v is, so according to theory, some constant times e to the t times eigenvalue times eigenvector. So C1 times e to the t times lambda 1, which is 1, times eigenvector 1 and 1, and plus C2 times e to the 2 times t, because the eigenvalue was 2, right? And everything times 1 and 2. Okay. So good. But our initial problem was a question about the function y. So our final solution should be y is just reading the first component of this resulting matrix. So C1 times e to the t plus C2 times e to the 2t. So this is going to be your solution. Okay. Okay. All right. So again, we will be discussing the stability of the differential equations, just we did in the difference equations. Well, I have this differential equation, y prime is a times y. And let me suppose that A allows a diagonalization. So then the solution y is c times the e to the eigenvalue times eigenvector, well, suppose that my eigenvalue, the j's eigenvalue, lambda j, is aj times I times bj. Yeah, here, so the eigenvalue can be a complex number. So this is the real part, and this is the imaginary part. And well, in order to find the solution, then I will need to raise this guy t times of lambda to the exponential function. So e to the lambda j times t is ajt plus I times bjt. But according to the Euler, so this is e to the ajt times cosine bjt plus I times sine bjt. Well, the magnitude of this complex number is this guy times this, magnitude of this guy times magnitude of that, but the magnitude of the second factor is always 1. So the magnitude of this guy. So, well, actually this number itself. So this is going to be the magnitude of this whole complex number, right? Okay, so the thing is, also we are also interested in the asymptotic solution of this differential equation. So in other words, we are interested. The question is, what will happen if t goes to infinity? If my t goes to infinity, then the asymptotic behavior will be depending on this number aj, right? If aj is a number which is greater than 1, then some of this term will eventually go to positive infinity. Therefore, this solution will eventually blow up in the critical condition. But on the other hand, if aj is a number which is less than, sorry, what did I say? Sorry, I messed up. Sorry. If aj is a number greater than 0, then it will go to positive infinity. But if a number aj is a number which is less than 0, then eventually the term associated with this exponential function will eventually tends to 0. Therefore, yeah. So it won't have any effect to the final asymptotic behavior of the solution. So this is the right time to give you this definition on the stability of the system of differential equations. And we say a system of differential equation y prime ay is a stable differential equation, stable system, and ETA goes to 0 if real part of every eigenvalue is strictly less than 0. If this is the case, then every term will tend to 0 as t goes to infinity. Therefore, the magnitude of your solution will eventually phase out to 0, right? So therefore, your ETA solution will go to 0. On the other hand, suppose that suppose that most of the real part, so most of the eigenvalue has real part less than or equals to 0, but also suppose that there is some eigenvalues whose real part is precisely 0, right? Then what do you guess? If that is the case, if the real part is strictly less than 0, then terms associated to these eigenvalues will go to 0. But if I have if there is such an eigenvalue whose real part is precisely 0, then the magnitude of this guy is what? Is 1, right? So this is going to be 1. Then in this case, this solution will never tends to 0, nor never goes to positive infinity, but it will somehow revolve around the origin, right? Right? Because this is the cosine and sine factors. So these terms is precisely these two terms means the rotation, right? So in this case, most of terms will tend to 0, but some terms associated to these eigenvalues will eventually revolving forever. Okay. And finally, the unstable and unbounded. So if there is any eigenvalue whose real part is strictly greater than 0, then the terms associated to this eigenvalue will go to positive infinity. So yeah, that's that. So unstable and unbounded. Okay. Okay. So for any given system of differential equation, y prime is a times y. So can you figure out the stability of your differential equation without solving it? If the size of A is small enough, then maybe yes. So precisely, if A is a 2x2 matrix, then we can actually determine the stability of this differential equation even without solving the problem. Okay, I'm going to show you how. Well, suppose I have this differential equation. It's two unknowns and two equations. And we'll be assuming that A, B, C, D, they are all real numbers. The characteristic polynomial of this matrix is A times lambda, A minus lambda times D minus lambda minus BC, and which is this. Solving this, and writing in descending order, you're going to have this looking polynomials. Oh, but hold on. This coefficient A plus D is the trace of the matrix, right? And AD minus BC is the determinant. So simply, I always say lambda squared minus trace times A is lambda plus determinant equals to 0. So we are supposed to solve this differential equation, this quadratic polynomial. And the root of this quadratic polynomial is trace plus minus square root of trace squared minus 4 times determinant of A. Everything divided by 2 by using the quadratic formula. You know that, right? Okay, so I have two solutions. And when this function, so when this system is stable, when this differential equation is stable, so differential equation is stable if and only if the real part of two eigenvalues are strictly less than 0, right? Okay. Hold on. So what is the real part? So in order the real part to be 0 or less than 0, then trace of A should be negative. And if determinant is also negative, then that implies this discriminant should be positive. So therefore, which means it has two real solutions, right? But determinant is actually the multiple of two eigenvalues, right? And determinant is less than 0 means one eigenvalue is positive and the other eigenvalue is negative, right? So that cannot be stable system. So we require the determinant, and so we can say determinant cannot be negative. So determinant has to be always positive. It's just in order to be stable system, right? So it turns out the system is stable if and only if the trace is negative and determinant is positive. So, well, precisely here. Yeah. This is very confusing diagram, but so this x-axis is means the trace of A, and the y-axis is the determinant. And this parabola it means A is a line, so which means the trace of A square is precisely 4 times of determinant A. So every point at this parabola means the discriminant equals to 0, right? And if trace is negative and determinant, and if anything, any point above this parabola means complex eigenvalues, and any point below this parabola means the real eigenvalues, right? And in order to be stable, then my matrix, the trace and the determinant of my matrix A must belong to the second quadrant of this diagram. Okay. So therefore, you can determine the stability of your system just by looking at the trace and the determinant of your original system without solving. Okay. All right. And the last exercise in this section is regarding the real matrix with complex eigenvalues. In that case, how would you compute the matrix exponentials? Yeah, that is a very interesting question. Also, well, you can compute the matrix exponential using exactly the same algorithm that I have shown you before, but I know some of you doesn't want to deal with matrix of complex numbers. So in this exercise, I'm gonna make everything real values functions. Okay, suppose that this is my system of differential equations, A and B, and this is the initial condition, and the characteristic polynomial is lambda square plus 1. So therefore, this is a irreducible quadratic, so it has two complex solutions. The first one is I, and the other one is minus I, and this is the eigenvalue, and this is the another one. So our solution should be something like this. So C times e to the t times the first eigenvalue times first eigenvector plus another constant C2 times e to the another eigenvalue times another eigenvector. And where C1 and C2, these are some arbitrary constant, depending on the initial condition, y0. Well, this is my initial condition, A and B, right? Sorry. This one should be U, sorry. So, so C is M inverse times U0. Therefore, MC is U0. So, and this M, the columns of M are the eigenvectors of matrix A. So this is M and this is C, this is AB. Therefore, C1 and solve, you can easily solve this. C1 is this number and C2 is that number. This is just a matter of computation. So U is C1 times this guy, but according to Euler's formula, e to the it can be written as cosine plus I sine, right? And times this eigenvector plus C2, which is this, times, now this is minus it, right? So this is cosine minus I sine t times the second eigenvector, 1 and I. And this is just a tedious computation. So I don't want to spend too much time explaining this. So it turns out the resulting thing is some combinations of the trig functions, A cosine minus B sine, A sine plus B cosine. So which can be written as like this. Oh, hey. So and this is the solution. This is the solution. And this one should be written as matrix exponential times the initial condition. And this is the initial condition, right? So therefore, this guy is the matrix exponential written in real values functions, right? Okay, so because the point is, if your eigenvalues are the complex two, if you have two eigenvalues of complex conjugate, then your matrix exponential may be involving some terms about these rotations. So complex eigenvalues means always rotation. All right. So, okay. So I have some time left. 여러분, 그런데 이제부터 좀 진짜 중요한 거예요. 잠깐만요. Okay, so I have some time left, and I really want to discuss this remaining time in Jordan forms. So Jordan form is a very special type of matrix invariant. So so we already discussed the matrix invariant. So, well, in order to be matrix invariant, two similar matrices must have a same matrix invariant, right? So, if you can see, so if you have two matrices with different matrix invariant, then that means those two matrices can never be similar to each other, right? So that is the idea of the matrix invariant, right? But it would be super nice, super great if we can develop a matrix invariant which completely determines the similarity relations of the matrices. In other words, I really want to have a matrix invariant such that the matrix invariant are the same if and only if two matrices are similar, right? The both-sided implications. If I can find such a nice matrix invariant, then just by computing the matrix invariant, then I can completely tell if two matrices are similar or not, right? If I have such a nice matrix invariant, that would be really nice, okay, right? And Jordan form is that matrix invariant. So like this. So if suppose I have two square matrices, and if those two square matrices have the same Jordan form, same matrix invariant called the Jordan form, then I am 100% sure that these two matrices are similar to each other. So this is very important matrix invariant. Well, there is an algorithm to compute the matrix, the Jordan form of any given square matrix A. Yeah, although the time that algorithm is super inefficient, but well, I'm pretty sure that the algorithm terminates in finite time. So that is a very nice algorithm. So, okay, so today I'll try my best to explain the Jordan. So, in order to understand the Jordan form, so then first you will need to understand the Jordan block. So what is a Jordan block? Jordan block is a square matrix. Jordan block of eigenvalue lambda is the matrix that looks like this. So this is an n by n matrix. So this dimension is n. This dimension is also n. And this is I say this is an almost diagonal matrix. Not completely diagonal. So every diagonal entries are lambdas, but just one entry above the diagonal. So I have a bunch of ones from here to there. And all the other entries, they are considered zero. This is my Jordan block. Okay. So this is a Jordan block of, I would say this is Jordan block of size n. And so these are typical examples of the Jordan blocks. So this is Jordan block of eigenvalue lambda of size 1, and Jordan block of eigenvalue lambda of size 2 and size 3. So these are, I have all diagonals are lambdas, and one entry above, they are all ones, and all the other guys, they are zero. So these are Jordan blocks, right? Okay. Now, Jordan form is a square matrix whose diagonal, the square block matrix, where each ji is a Jordan block. So Jordan form is, roughly speaking, so square matrix consisting of Jordan blocks. So just like this. So each of these Jordan blocks, they are Jordan block of any arbitrary size of any eigenvalues. And these eigenvalues may or may not be the same. So I mean, the point is, so these are diagonal block matrix whose diagonals are the Jordan blocks. So this is the Jordan block. Okay. Okay. And as always, all these empty entries should be considered zero. And this theorem is probably the most important theorem, but I don't have enough time to prove this. So let me take granted. Every square matrix is similar to some Jordan form. Not a Jordan block, but Jordan form. A Jordan block, a single Jordan block, it should be also considered as a Jordan form, very special type of Jordan form. But you know, every square matrix is similar to some Jordan form. So why is it important? Suppose that you have two matrices. Suppose that you have two matrices A and B, and suppose that these two matrices have the same Jordan form. Then according to the theorem, then we are safe to say if two matrices have the same Jordan form, then those two matrices must be similar to each other, right? So if A is M1 times Jordan form, which I would say, and B is M2, J M2 inverse, then A is M1, M2, B, M1, M2, right? Suppose that if A and B has the same Jordan form, then A and B, they are similar to each other. Okay. Sorry, I'm not 100% confident about what I just written. Okay, so I mean, so they must be similar. So in this sense, we say the Jordan form is a complete invariant of the matrix. if two Jordan forms have the same set of Jordan blocks but different order, but they are similar. Well, suppose that I have this Jordan form, and for instance, suppose I have this Jordan form and that Jordan form, and it has the Jordan block J1 and J2 in this order, and the other one has Jordan form J2, Jordan blocks J2 and J1 in this order. Even though even though it seems like they do not have the same Jordan form, but by using some permutation matrices, then those two orders can be fixed. And well, it is very easy to see that this guy is precisely the inverse of this, the first matrix. So those two guys. So so therefore, in order to discuss the Jordan form, then the order of the Jordan blocks doesn't matter too much. What really matters is the set of Jordan blocks that which consisting the entire Jordan. Well, now I have a single Jordan block of eigenvalue. So this is Jordan block of size n with eigenvalue lambda 0. And this guy has only one distinct eigenvalue lambda 0, right? Well, this is very easy to see because just consider the characteristic polynomial of this matrix J, the Jordan block J. Then it has only one root, lambda 0. And what do you think is this algebraic multiplicity? Is n, right? Because its characteristic polynomial is precisely lambda 0 minus lambda raised to the power of n. So it has only one eigenvalue lambda 0, and its algebraic multiplicity is n. But the interesting thing is its geometric multiplicity is exactly 1. So least possible geometric multiplicity. Well, the proof is very easy. Well, just consider its characteristic polynomial. So this is, and if you compute the determinant of this guy, which is lambda 0 minus n, so its algebraic multiplicity is n. And now we want to compute the geometric multiplicity or the dimension of the eigenspace of lambda 0. So j minus lambda 0 times I times x equals to 0 if and only if. So if this is j, so well, I just got rid of all diagonal entries like this. So what times this guy equals to 0, that. So which turns out that the system of equations, well, even though I have n equations down there, but the last row entirely consisting of zeros, right? So the last row is just vanishes. So I have only n minus 1 equations, okay? So x2 equals to 0, x3 equals to 0, and xn equals to 0. So therefore, this is the only non-zero vector that spans the entire eigenspace of lambda 0. So therefore, in this sense, for this reason, the eigenbasis, the eigenspace has dimension 1. So geometric multiplicity 1. Okay, so this statement is a very important statement. So let me try to explain this. Suppose that I have a matrix, and suppose that my matrix A has just one single eigenvalue, lambda 0. And suppose that this algebraic multiplicity, sorry, let me repeat. Suppose that I have, forget it, sorry. I have an eigenvalue lambda 0 whose algebraic multiplicity is k and geometric multiplicity is L. Suppose that I have such an eigenvalue lambda 0. Then the Jordan form of A must have some Jordan blocks of eigenvalue lambda 0. And the sum of sizes of these blocks equals to k. This requires some explanation, right? So if A has eigenvalue, then A must be similar to some Jordan form J, and this Jordan form may have bunch of eigen Jordan blocks like this, but it has eigenvalue lambda 0. So therefore, there must be some Jordan blocks whose eigenvalue equals to lambda 0, right? Maybe I have so lambda 0, lambda 0, and lambda 0, and lambda 0. Okay. And this guy has algebraic multiplicity k, right? If this guy has algebraic multiplicity k, then the sum of these Jordan blocks of eigenvalue lambda 0 should be k by k block matrix, right? So this is k by k. And it has geometric multiplicity L. And each block should contribute to geometric multiplicity 1, because when I proved that this guy has geometric multiplicity 1. So in order to have the geometric multiplicity L, then I will need to have L many Jordan blocks. And each Jordan block has geometric multiplicity 1. Therefore, in order to have the geometric multiplicity L, I will need precisely L many Jordan blocks of eigenvalue lambda 0. Why? Because A and J, they are similar to each other. So they must share the same set of eigenvalues. And these eigenvalues here. So if lambda 0 is an eigenvalue of A, then lambda 0 should be also eigenvalue of J. And if this guy has eigenvalue, so algebraic multiplicity K and geometric multiplicity L, and this guy also must have algebraic multiplicity K and geometric multiplicity L, right? And the only way to have the algebraic multiplicity K and geometric multiplicity L should be having these blocks as its members in this Jordan form. Okay. Okay. So, given an n by, so therefore, the most important question is, for any given square matrix A, we need to determine its Jordan form. How to find the Jordan form? So from now on, we'll be focusing on the case where A has only one distinct eigenvalues. If A has many distinct eigenvalues, then you can repeat the same procedure again on and on. So I will just focus on the case when A has only one eigenvalue. Right. So if B is similar to A, then B has only one distinct eigenvalue, which is the same as the eigenvalue of A. And this algebraic multiplicity and geometric multiplicities are the same as the algebraic and geometric multiplicity of A. So suppose that A is 2 by 2 and it has eigenvalue lambda. And suppose that this eigenvalue has algebraic, then in this case, there are only two possibilities. The algebraic multiplicity is 2 and geometric multiplicity is 2, right? So in this case, dimension is, so dimension of eigenspace 2. Now, what do you think is the Jordan form of this matrix? Well, algebraic multiplicity is 2. In order to have the geometric multiplicity 2, then I will need 2 Jordan blocks, right? And each of these Jordan blocks, but the sum of sizes of these Jordan blocks should be also 2, right? Because algebraic multiplicity was 2. So therefore, the only possible choice option is this. So this should be the Jordan form of the matrix A. The other case is the algebraic multiplicity of this guy is 2, but geometric multiplicity is just 1. Then since it has only one geometric multiplicity equals to 1, that means I will need the Jordan form of this matrix was just one single Jordan, right? because one single Jordan block means what geometry multiplicity 1. So this is the Jordan form of the matrix A. If A is 3 by 3, and suppose that this eigenvalue lambda has algebraic multiplicity 3 and geometry multiplicity 3. So geometry multiplicity 3 means I will need to have 3 Jordan blocks, and sum of sizes of these Jordan blocks must be 3, right? So this is the only possible scenario. Algebraic multiplicity 3 and geometry multiplicity 2. So geometry multiplicity is 2. So I will need to have 2 Jordan blocks, and sum of their sizes must be 3. So this and that. Or you can say Jordan block of size 1 and Jordan block of size 2, but you know, the order really doesn't matter. So this is the only possible scenario for this case. Algebraic multiplicity 3 and geometry multiplicity 1. So here, since geometry multiplicity is 1, so I will need to have only one single Jordan block of the Jordan form of the matrix. So this is the Jordan form of the matrix A. Okay, now things are getting more interesting. A is 4 by 4, and algebraic multiplicity 4, geometry multiplicity 4. Yeah, for some reason, I lost connection between the Apple Pencil. So in this case, yeah, so this is the only case. Algebraic multiplicity is 4 and geometry multiplicity is 3. So I will need to have 3 Jordan blocks whose size, the sum of size is equals to 4. And I guess this is the only possible option. And algebraic multiplicity is 4 and geometry multiplicity is 1. And I have only one single Jordan block. So this is the only possible option. And the most tricky case is algebraic multiplicity is 4 and geometry multiplicity is 2. Then I will need to have 2 Jordan blocks whose sum of size is equals to 4. And but I have these two cases. So then either this or that, right? Now, which one is true? How do I know which one is the Jordan form of A? So this will be discussed in my next lecture. Okay. 네, 죄송합니다.